So this is a review of lecture 22 on diagonalizing matrix, and we arrive at the last part, which is the Fibonacci, the difference equation, the UK plus 1 equal to AUK. So let me write that down, the formula that we want to focus on in this video. So let's define the U1 first. Let's see. So U1 will be the AU0, and therefore accordingly the U2 will be like AU1, but we know the U1 is AU0, so U2 is the A square of U0. So this is the matrix square, and thus we can continue on, and we know that we will have the U of k is the A to the power of k U0. So we know we interested, let's say, is a U of 100. That means we can just do this. Okay, now let's go further into, so what is the solution of U100, how to utilize the eigenvalue and eigenvectors that we have been learning so far to get to the solution. So let's do that. Okay, let me write that down here. So we have another form here that UK is A to the K U0 that we derive from here, of course. Okay, so U0 we can define, U0 is just a matrix, let's say, and then we can define them by having the combination of our eigenvector actually to the xn if we have the n eigenvector, and we can multiply some constant. So it's like those independent eigenvectors. Remember, if we have the n distinct eigenvalues and we have n distinct independent eigenvector, and those act like a basis on which we can multiply by some constant, and then we can get the U0, right? And then if I multiply the U0 by the matrix A, then I will have this. Okay. So what is A multiplied by my first eigenvector? Of course, we have those beautiful ax lambda x. So we will have, I will just plug it in straightforwardly, just as it is, and convert them directly here. C2 ax2, oops, I need to, and cn lambda n xn. Okay, cool. So what do we have here? So we have been learning so far that if I'm interested in the power of 100 of A, then the eigenvector didn't change, the constant of course didn't change, and what only affected this result is the eigenvalue. So that what I have been learning so far about the eigenvalue, right? So all the changes in A correspond directly only to the part of like the eigenvalues here. So only eigenvalues affect those the result of my A to the power of something. So let's write that down. Okay. So what we have here is we can write it in the matrix form as well. So what do we have here in the eigenvalues part? We have, of course, the big lambda, multiply them by 100 to the power of 100, I mean, and then we have the eigenvector here, right? We multiply them by the eigenvector. So, and we can put the eigenvector here on the left of it, right? So this will be x, because each lambda will be multiplied like the coefficient of each eigenvector. Remember what I did in the previous part. And then I will have a c here, which is also like the vector c, like c1, c0 to the cn in the column, and then it will act as a coefficient to these two. Okay, so this will be my term. So this will be like U of 100 U0. And actually in the book it goes further into it defines the c as, so if you goes from here, then we can also define here as u0 to the power of x and then c, and then we can define c as the x inverse of u0, so we can also have it express this in terms of x inverse and u0. Or if you want to be more general, then you can also have the a of k to the u0 is x a k x inverse u0. Okay, so this is the important formula that as well mentioned in the book. So let's get into some example to find some solution of a to the 100 and find a solution of what is the 100th term or of something. And we will use the Fibonacci number, and let me delete this for a sec. So let's continue. So let's say I have my Fibonacci here. So we know the Fibonacci series is the first 0 and then 1 plus 0, then you got 1, and 1 plus 1 is you got 2, 1 plus 2 you get 3, 4, 8, 13, and so on. And then let's say I want to know, I'm interested in the 100th term, right? Now we can use this formula, but how? So first let's just define like the formula of this series, right? So we have like, let's say this term, the 1, 2, 3, or let's call this 0, 0, 1, 2. So the second term is the first term times the 0 term, right? So f2, if k is 0, then f2 is f1 plus f0, which is 2 is 1. I'm sorry, I mean, yeah, it's okay, 1 plus 1. So in this case, there will be 3, right? If I count from 0, then this is 2 and this is 1. So my third term here will be the second term times the first term. Okay, so that's pretty clear. Okay, let me quickly delete that. So I have defined this one, some sort of like the general formula, and I can also, like, just a trivial thing, have fk plus 1 equal to fk plus 1. And now you kind of see it, you kind of see where I'm going. So this is kind of look like the matrix, right? And let's define some vector u. So u is equal to the fk plus 1 and the fk, and this uk. Okay, so I can now express my uk plus 1 equal some matrix A times uk, which is what we are interested in this part, right? uk plus 1 equal A times uk. So uk plus 1 is what? So you have fk plus 1 here in the uk, so this will be plus 2, this will be fk plus 1, this will be some matrix that we're interested in, and this will be my uk, fk plus 1, fk, right? So what is fk plus 2? Oh, we have it here, right? So we just fill this matrix out just to comply with this equation. fk2 is 1 of fk1 plus 1 of fk only. I don't need to add plus there. Okay, so 1 of this, 1 of this, and then the fk1 itself is just some trivial, okay, fk1 equals to fk1 and 0 of this, right? So this is our matrix A, this is our uk, and this is our uk plus 1. Cool. Now we have our matrix A. Now in this chapter we are always interested in the eigenvalues and eigenvectors, and let's find them. And I will not do the computation, it kinda messy, but you can do it yourself, and it's also actually the example in the book and also in the lecture. So I'll just go right away and say that the first lambda is 1.618 and the second lambda is the 0.618, and then the first eigenvector is the lambda of 1 1, and the second is the lambda of 2 1. Okay, now let me delete this one first because we don't need this anymore. Okay, now you see that actually currently we already can know like the rate of growth of this Fibonacci. So you see that the Fibonacci series growth, but they're not double. They're not like 2 is not double to 4, but they're in some terms that less than 2, I guess, or maybe something, but they're positively growth, right? And what is that rate of growth is this one actually, the lambda that is positive, that is bigger than 0, but the positive value. Instead, this one, as imagine that as this is this will bring the system to the 0 eventually, because remember in the previous part that the negative or the absolute value of lambda less than 1 will bring the system to stability, right? And let's try to find a solution for this one first. Okay, let's forget about that one. They're just like some side examples, admission that you, by finding the eigenvalues, you already know like the growth of the system right now. Okay, so let's find the 100 term right here. So we can just plug it in here right away. So because we only have 2 eigenvector, then we can just use this until the second one, which is up to here, right? So let's write that down. So we have our k term. So 100 0 is C1 times lambda 1 is 1.618 times the x1 is lambda 1 1, and this constant 2 times lambda 2 which is minus 618, and the second eigenvector. Okay, so this is my general solution for the k term. Remember that this UKU is actually UK, so this is actually my UK. So I can find the 100th term with this formula right here. Okay, but I still need to find the C1 and C2. And how can I find that? By utilizing the 0th term. So what does that mean? What does that mean? I'm sorry, I'm blabbering about. So what this mean is that we bring the lambda factor to the 1, right? Because the lambda is k actually, if you see it here. Let me just delete something so that you can see better. So let's do it right here. So what happened, what is my 0th term, which is here, right? So I define the UK before as, you remember in the matrix, I define my matrix UK as the fk plus 1. We're still talking about the Fibonacci one here, and fk. So my u0 will be the f of 1 and f of 0. So that will be 1 0. Okay, and then my UK, remember that UK is a of ku0, but then my UK, I get the formula here, C1 of lambda k x1 plus C2 of lambda k C2 x2, I mean. So the u0 will be C1 of lambda 10 x1 plus C2 of lambda 20 x2, and this is going to be 1 because power of 0, then it will be 1. This will be also 1. So you can find the constant by looking at the 0th term or the initial condition. This is the initial condition. Okay, so you'll have 1 0 is C1 times the lambda 1 1 plus C2 times lambda 2 1, and there you have it. You can find the C1 C2 and you can have the general solution to find the 100th term in the Fibonacci number. Okay, one last thing. You see that here I'm multiplying by 100, right? I just want to bring you attention quickly to the rate of growth. So this number will slowly becoming 0 because it's just point something that is less than 1 and it will become 0, and then eventually this lambda, this UK, this one term will converge to something that is only consists by this term. Okay, so that's it for lecture 22. Thank you.